Today we are discussing some fundamental concepts that play a central role in electric circuits. So we're going to start off with an overview of the units of the metric system, fundamental and derived units. We'll describe engineering notation, and the idea of significant figures. Then we'll cover electric charge, current, and voltage, which will play a central role in this course. And finally, we'll introduce the idea of a two-terminal device and briefly describe how we would make measurements of electric current and voltage. So we begin with the current metric system, the International System of Units, or called SI units from the French version of International System. In SI units, we have some physical quantity. This will be described as some number, some pure number, x, in some sort of notation. It could be scientific notation, or we'll mostly use what we call engineering notation. And then a unit, okay, like meters or seconds or kilograms or things like that. Now, in the SI system, there are 7 fundamental, what we call base units. And from those base units, we can then come up with what we'll call derived units. In principle, everything could be described in terms of the base units, like seconds, meters, and so on. But there are certain combinations of those that occur so often, like the unit watt for power, that we end up with so-called derived units. Now, the way that the base units are defined currently might seem a little strange, but let's look here, definition. Base units. These are defined so that we can get the maximum precision in measuring them. All right, that's the fundamental thing we want to have in our definition of base units. We want to be able to determine those values as precisely as possible. So sometimes that leads to rather strange definitions, at least unless you work in a fundamental physics laboratory. So let's turn to these now. Our first unit is that of time, and it is the second. And we represent that by a lowercase s. Now, it used to be defined as 1 over 24 times 60 times 60 of a solar day. What is a solar day? That's the amount of time it takes the sun to go from the same position in the sky. Say at noon, it's the most highest above the horizon, and then we go a full day when the sun comes back to its original position. So that's a little different than the time it takes for a star to return to the same position in the sky. That would be called a sidereal day. Okay, and then this is just the idea that there are 24 hours in a day and 60 minutes in an hour and 60 seconds in a minute. Okay? So for most of history, that was the definition of a second. But it turns out that the Earth does not spin at an absolute uniform rate. Over time, it slows down very gradually, but also even during, from year to year, it can slightly speed up or slightly slow down due to changes in the internal configuration of the Earth. So the way the second is now defined is 1 second is by definition 9,192,631,770 cycles of a particular transition of the cesium atom. Okay, and how is this measured? Well, you set up a cesium atom so that it undergoes this particular transition, which emits a microwave signal, and then you measure the number of cycles of that microwave signals. That is the basis of so-called atomic clocks. And so we use atomic clocks to define the second because that is more precise than using the rotation of the Earth. Then we have length. Basic unit is the meter. Lowercase m is the abbreviation for that. Now this used to be 1 over 10 million times the distance from the North Pole to the equator through Paris, France. That couldn't be measured very precisely, so then eventually a so-called International Prototype Meter bar was developed with 2 scratches on it that defined the meter, and then copies that was kept in Paris and copies were distributed to other countries. And then eventually it became defined in terms of a certain number of wavelengths, of a certain wavelength of light. And today, it's fixed by defining the speed of light, c, to be exactly 299,792,458 meters per second. We've already defined the second, so if we define the speed of light, this then defines the meter. By the way, in the United States, sometimes we use U.S. customary units, and these are defined in terms of metric units. So, for example, one inch is defined to be 25.4 millimeters exactly. And from that, you can work out things like miles and yards and so on. Okay, so time, length, mass. Fundamental unit of mass is the kilogram. And why is it something that has a prefix like kilo instead of gram? So there's historical reasons for that. We won't worry about it here. And it's represented by kg, kilogram. at one time was defined as the mass of 1 liter of pure water at a given pressure and temperature. Later, it was defined as the mass of a certain lump of metal called the International Prototype Kilogram. These days, we'll just jump to how it's defined today. This one looks kind of weird. It's defined by fixing, by definition, a certain physical parameter called Planck's constant, h, to be defined as exactly 6.62607015 times 10 to the minus 34 kilograms meters squared per second. Since we've already defined the meter in the second, this then defines the kilogram. Now that looks really obscure, but this constant comes up a lot in quantum physics, and it can be measured with extreme precision. So remember, the whole idea is we want to define units so that we can actually measure them with extreme precision. Okay, next we come to electric current. And the unit there is the ampere, or capital A, or its abbreviation. And this used to be defined as the force between two wires carrying 1 amp of current was a certain amount. It's now, today, we'll just jump to this, we define the fundamental electric charge, E, be exactly 1.602176634 times 10 to the minus 19th coulombs. That is the charge on 1 proton, or the negative of the charge on 1 electron. And then we say that 1 amp is the flow of 1 coulomb per second. So those are the 4 fundamental units we will use: time, length, mass, and current. There's 7 fundamental units. The other 3 have to do with temperature, amount of substance. Right? The temperature is the absolute temperature is defined in kelvins. The amount of substance is defined in moles. You may cover that in your chemistry course. And luminous intensity, the candela. Okay, so we don't make use of those 3. So we use these 4. So now we turn to derived units. These are units of convenience. They come up a lot, so we give them special names. They're all defined in terms of the fundamental units, but it's just very convenient for us to have these derived units as kind of a shortcut. So we have force. The unit is the Newton, represented by capital N, and it's defined as 1 Newton equals 1 kilogram meter per second squared. It is the force which will cause 1 kilogram of mass to accelerate at 1 meter per second per second. So after 1 second, it'll be traveling at 1 meter per second. After 2 seconds, 2 meters per second, and so on. And right, this comes about from Newton's second law of motion. Force is equal to mass times acceleration. By the way, the acceleration on Earth gives rise to a particular force that we call the weight of an object, and that would just be the mass times the acceleration due to gravity, where the standard acceleration due to gravity is defined to be 9.80665 meters per second squared. Then we have the idea of energy, and the unit is the joule, represented by a capital J. It is defined as 1 joule equals 1 Newton meter. And this comes from the idea, from physics, that the work done by a force is equal to the force times the distance through which the force operates. So the joule is the unit of energy, the unit of work. And then we have power. And the unit is the watt. Notice these are, Newton, joule, and watt. These are names of different people. But when they're written as units, we do use lowercase for the first letter. Abbreviation is capital W. And the watt is defined as 1 watt equals 1 joule per second. So if you expend energy at a rate of 1 joule of energy per second of time, that's 1 watt. Now, in electricity and electrical power, a watt is really a pretty small amount of power, and the joule is a very small amount of energy. We often then have another derived energy unit we call the kilowatt hour. And as the name implies, 1 kilowatt hour is the amount of energy you get if you have a kilowatt, which is 1,000 joules per second, acting for 1 hour, which is 60 times 60 is 3,600 seconds. Okay. And so you work that out. A kilowatt is a bit more than a horsepower, so this is a bit more than a horsepower operating for 1 hour. And just multiply those out, that's 3.6 million joules. And that's, currently where I live, it's about 10 cents, 10 US cents per kilowatt hour. So that's a more useful amount of energy when you're talking about energy use in a household or an industry or something like that. Then we have pressure. The unit is the Pascal. This requires 2 letters, capital P, lowercase a. And it's the unit of pressure. It is defined as 1 Pascal is a force of 1 Newton per square meter of surface area. And finally, we have the unit of electric potential energy. That is the volt, represented by a capital V. And that is defined as 1 volt is 1 joule per coulomb of electric charge. So we'll later talk about a hydraulic analogy with electricity. You can think of this as like an electric pressure. It's kind of how strongly charges are either repelling or attracting each other. So now we turn to the topic of engineering notation and the idea of significant figures. So first, you've probably learned about scientific notation. And this is where you would represent a physical quantity as some number x times 10 to some exponent n, and then you'd put units. And x is a real number between 1 and 10, and n is some integer. It could be positive or negative or 0. All right, so we have, for example, might have a force of 1.234 times 10 to the minus 2 newtons. Okay, that would be scientific notation. The exponent n we can call the order of magnitude of the quantity. Okay, so this is always, and of course it's possible to define forces and lengths and things to be positive or negative. So you could have a plus or minus in front of this You want it to be a little more precise. But it's always a number in magnitude anyway that's between 1 and 10. And then you use 10 to some exponent to represent the order of magnitude. That's scientific notation. It's very systematic and formal, but it has some drawbacks for engineering work in that as quantities change, say just by a factor of 10 or so, you're always changing this exponent. And it's easy to overlook that, and it can be a little confusing. So for engineering work, we often use engineering notation, which is a variation. So in this system, we would have, it could be a plus or minus if you needed to, and then a number x, and then a prefix, and a unit, or units, depending on as the case may be. And these prefixes represent exponents of the form 10 to the 3m. Okay, so in other words, it's like scientific notation, but the exponents are all factors, or multiples rather, of 3. They have a factor of 3. And we give them a name instead of writing this notation. So, name, and then a symbol, and then the value. So for example, pico, represented as P, has the value of 10 to the minus 12th. Just a few of them. There's a complete list given in the PDF notes. Milli, lowercase m, has a value of 10 to the minus 3, like a millimeter, picometer, picosecond, things like that. Mega, capital M, has a unit, a value of 10 to the 6th, and so on. So let's look at our force up here, 1.234, 10 to the minus 2. So we would say 1.234 times 10 to the minus 2. We want to represent that as something times 10 to the minus 3. And this x should be between 1 and 1,000. Okay? So this is already something almost just a little bigger than 1. So we want this to be either 10 to the 0 or 10 to the minus 3. Those are our options. So if we made this 10 to the minus 3, so we reduce this by a factor of 1 over 10, we'd have to increase this by a factor of 10. So that would be then 12.34 times 10 to the minus 3. And so when we put in the units, then we would say that F, in this case, would be 12.34, 10 to the minus 3, that's milli, so millinewtons. Okay, an advantage of this is that very often we'll end up, say we could have, like 5 millinewtons, 12 millinewtons, maybe 240 millinewtons, but often all of our forces will all be millinewtons, represented as millinewtons. So it's easier to keep track of the relative magnitudes because it will just show up as differences in this number x. Okay, so that's and we don't have to write the times 10 to the plus or minus n and so on. Okay, so this is engineering notation. All right, now we turn to the idea of significant figures or significant digits. So to motivate this, suppose I tell you that I go and measure the length of something and I report it back to you as x is equal to 1.53 meters. So does that mean that the length x of some object is exactly 1.53 meters? No, you can't measure a length exactly. So how well do we know the length? Well, since I gave it to you in the nearest hundredth of a meter, that is the nearest centimeter, you can assume this is to the nearest 0.01 meter. Okay. So, and I visually rounded it to the nearest 0.01 meter or the nearest 1 centimeter. Which is in engineering notation, 10 millimeters. Okay. Now, maybe, we have a tape measure and it has, these are centimeter readings. And then in between, we've got millimeter markings. And let's say, so let's see, 1.53, that would be 153 centimeters. So maybe this is 153, this is 152, this is 154, and here we'd have like this. So if I reported 153 centimeters, 1.53 meters, you can assume that the actual length was somewhere between 153 minus a half or plus a half centimeters. In other words, you can assume, if I measured correctly, that x is 153 plus or minus 1/2 centimeter. So my original measurement in meters would be 1.53 plus or minus 0.005 meters. Okay, and this is 5/1000th of a meter, or 5 millimeters. So you can assume, right? So here's 1, 2, 3, 4, 5 plus, or 1, 2, 3, 4. Actually, put one more there. 1, 2, 3, 4, 5 below 153. Okay, and so I just rounded it to the nearest centimeter. Now, maybe I could have been more precise and really tried to visualize it to the nearest millimeter. And let's say then I report to you that x is 1.530 meters. Is that any different from my reporting that the length is 1.53 meters? Well, mathematically it's not. 1.530 is the same as 1.53. But when I use that to report a measurement, the implication is I measure that to the nearest last digit, which in this case would be 1/10, 100th, 1,000th of a meter, so to the nearest millimeter. Where up here, 1.53, you would assume I measured to the nearest centimeter. So this has 1/10 of the uncertainty in the measurement as the previous one. So we say this measurement had 3 significant figures, or SFs, whereas this measurement had 4 significant figures. So it's much more precise. Now, formally, if you probably have taken a physics lab and you had to make measurements and report them with an uncertainty, the rigorous way to do this would be to say, you give some value x, maybe is equal to 1.53 plus or minus 0.026 meters, something like that. You actually formally put an uncertainty in there. All right, and if you want to be very precise with measurements, that's what you would do. But for engineering work, often we just let this be implicit by assuming that this means that the last digit is a rounding of the actual value, so that the uncertainty is plus or minus 1/2 of the last digit. So if this is the case, the last digit is 0.01 meters, that would be an uncertainty of plus or minus 0.5 centimeters, or 5 millimeters. Okay, so that's the idea of significant figures. More significant figures means more precision. Our standard, or we'll just say the default for us, which is a pretty good default for engineering work, is that answers will have we'll have answers with 3 significant figures. Okay, so that's better than 1% error or uncertainty. Now, when you're doing calculations, if you keep rounding numbers and doing calculations, you build up what's called round-off error. And so to try to avoid that somewhat, for calculations, the intermediate calculations that you do, keep at least 4 significant figures. And then when you finally get to the end, round it to 3 significant figures. Of course, if you're doing all of the calculations in a calculator or on a computer, and where you can actually keep the intermediate results in the calculator or computer, you might have 16 digits of accuracy. But if you're going to write it down and then do further calculations, keep at least 4 significant figures for intermediate calculations. And then finally, report with 3 significant figures, unless you're told otherwise. That's our assumption, our default for this course. Now we turn to the topics of electric charge, current, and voltage. So the idea of electric charge is an ancient one. People observe what we still can observe today. If you take, say, a plastic comb and you run it through your hair, you might notice that it attracts little pieces of paper. We call it static electricity. And in fact, ancient peoples knew that if you took, say, a piece of glass and a piece of resin, which is basically a fossilized tree sap, you rub them together, they would attract each other. But if you did the same thing with another piece of glass and another piece of resin, so let's just do that here. You rub them together, and you would notice they would attract each other. But if you did that with another piece of glass and another piece of resin, and you put the 2 pieces of resin near each other, they would repulse each other. And likewise, the two pieces of glass would repulse each other. So if you think about the way in which masses attract, all masses attract each other. There's no repulsion, gravitational repulsion. So the fact that you have both attraction and repulsion indicates that there's 2, we call this phenomenon, static electricity, or due to an electric charge. It indicates that there are 2 types of electric charge. And the glass charge, we just, for historical reasons, call plus or positive charge. And the resin we write as negative or negative charge, minus or negative charge. And if you then study this in detail, which wasn't done until in modern times, people tried to quantify this. You find that if you have 2 positive charges, Q1 and Q2, and they are separated by a distance r, then they will repulse each other with a force F, such that F is equal to product of the charges, Q1 times Q2, over a constant, which we write as 4 pi epsilon 0, called the permittivity of free space, times the square of that distance. Okay, which looks, we know that gravity falls off as 1 over the distance squared. So does the electric force. But here it's a repulsive force. Now, if on the other hand, you had a positive charge Q1 and a negative charge Q2, well, then this force would be attractive, right? And so we would say then the force would go in this direction, and we would write that the force would be let's explicitly put a minus sign here, so all the Q's are positive, and then a negative charge would have a minus sign explicitly. Q1 times Q2 would have a minus sign, minus Q1 Q2 over this same factor. Okay, so this would be attractive force. A negative repulsive force would be an attractive force. And how would you figure out what these charges actually were? Well, you could take one charge that you define to be one coulomb is our unit of charge, and then you could make these force measurements, and since you know Q1, you could determine Q2. All right, so that's the basic idea. Now, the electric force drops off as 1 over the square of the distance, right? So very similar to gravitational force, right? So, gravitational force we usually write as a constant g, the gravitational constant, times the product of the masses over the distance squared. So the constant here we write as 1 over 4 pi epsilon 0 for various practical reasons. But in gravity, the masses are always positive. We don't have negative mass. Okay. Now, we mostly ignore electric charge in our day-to-day life unless we get a static shock. Right? We go and scuffle our feet along a carpet and touch a doorknob and we get a little shock. And the reason is that most material is electrically neutral. So we now know most of the positive charge is contained within a very, very tiny nucleus, which also contains most of the mass of an atom. And then around that is a cloud of electric charge. And these cancel each other out. So if we're out here, if we put a lone charge out here, there would be a repulsive charge between the positive charges, the nucleus and this positive charge. But then there would be an attractive charge between the electron charge and that positive charge, and these two charges would cancel out. Okay, and so most matter is electrically neutral, so we don't notice electric forces. Electric forces are much, much more intense than gravitational forces, but because everything responds to gravitational forces and there's no repulsive gravitational force, we really notice gravitational forces. We don't generally notice electric forces because, again, they only arise when there is an imbalance of charge, isolated positive or negative charges. Okay, so let's go back to this picture where we have two positive charges repulsing each other. If I want to move this charge Q2 closer to Q1, I'm going to have to push on it to overcome this repulsive force. And I'm going to have to do work to move it closer to charge Q1. So let's redraw our picture here with an x-axis. And at the origin, we'll put a charge and we'll call it Q0. And then over here, somewhere, say at a value x1, we'll put a test charge, Q sub t. And then if we have this repulsive force F, and we want to move our test charge to, say, a position x2, which is closer to the other charge, well, we're going to have to overcome this force. So we're going to have to push with a force minus F to overcome that. And then we're going to move, integrating a bunch of dx's, little differential movements to get from x1 to x2. Okay, and the force of repulsion is the product of the charges Q0 and Q test over this constant 4 pi epsilon 0 times the square of the distance. And the way we've drawn it with Q0 at the origin, the distance is just whatever the x coordinate is. So this would be the force. So now if you have a force times a displacement, that's an amount of work. So dW is minus F, the force that we have to apply to overcome this positive repulsive force. and then the little displacement dx. So if dx is negative, we go to a smaller value of x, then you're going to have negative times negative is going to be positive, and that's going to be a positive amount of work we have to do. If we allow x to increase, that would be dx would be positive, then negative times positive would be negative. We would do negative work, meaning that the electric field would do work for us. It would do work on this charge. It would accelerate it, or we could extract that work. All right, so now we can just say that the work required to go from x1 to x2 is, we're just going to integrate this expression. So we're going to have the minus sign there. We'll put that out in front. And then we've got q0 qt over the constant 4 pi epsilon 0. And then we integrate from, let me do that a little better. Integrate from x1 to x2 dx, and then over the x squared there. Okay, so the integral of 1 over x squared is minus 1 over x, and then you evaluate from x1 to x2 and work that out, and this is what you get. q0 qt over 4 pi epsilon 0 x2 minus q0 qt over 4 pi epsilon 0 x1. This is the energy or the work required to move the charge from x1 to x2. And it's the difference of these two quantities. And so this leads us to define each of these as a potential energy. The potential energy of the test charge at position x2 and then at position x1. And so the difference of these potential energies then represents the work that we have to do to move the charge from x1 to x2. Okay, here with x2, right, would be smaller than x1, so 1 over x2 would be bigger than 1 over x1. This would be positive with a larger magnitude than this negative number. So this would be a positive quantity. That's what we've shown here. We'd have to push, we'd have to do positive work to move the charge from x1 to x2. Okay, now what we then do, right, is we're going to define potential energy per charge, per unit charge, per coulomb, sorry. We'll call that V of x. V is going to be a voltage. And we'll write this as V of x2 minus V of x1 times the charge on the charge we're trying to move, the test charge. And what will V of x be? It will be everything in this expression, except the qt, because we're factored out the qt. So it'll be q0 over 4 pi epsilon 0 x. Now, we can always add a constant to an energy, because if we're taking a difference, then that constant will subtract out when we take the difference. So this is just some other energy. And we'll call this V infinity, because when x goes to infinity, 1 over x goes to 0, this term goes to 0, and we're just left with V is equal to V infinity. So that will be the potential at infinity, when the charges are infinitely far apart. And we could take that to be equal to 0, but not necessarily. We could choose something else as our 0 voltage reference. So this is our voltage. Voltage is joules per coulomb, potential energy per unit charge, right? And this is where we define a volt to be 1 joule of energy, right? This is an energy, and then we divide it by charge. So energy per charge. So now let's talk about electric current. And let's assume this is a piece of wire here. And we have some positive charges in the wire. And we've got some negative charges in the wire. The wire is electrically neutral. But suppose the positive charges are able to move, and they move to the right with a velocity v. And we choose some plane as a reference surface through this wire, and we ask, in 1 second, how much charge moves to the right through that plane? Well, in general, if these charges are moving with velocity v, then in a arbitrary time t, they're going to move a distance v times t. So in a time t, whatever charges are between these two lines are going to move across this green reference line. Okay, so we're going to say that the current I is equal to, well, let's let there be n sub L charges per meter. That's the number of these per meter. Okay, and then this is meters per second. The current I is going to be the number of these charges per meter times the charge on each of them. And here we'll just assume it's like a single proton, so that's the elementary charge. Times the number of meters per second. Okay, so how does this work out? This becomes charges per meter times the actual number of coulombs per charge times meters per second. Works out to just be then coulombs charge per second flowing past that surface. And we define that to be the current in amps, right? So this was our idea that one amp is 1 coulomb per second flowing across a reference surface. Now, what if instead, in the same wire, we had these positive charges and these negative charges? And instead, the negative charges were moving, and they moved to the left with a velocity v. And we draw this same, say, reference plane here. So now charges are going to be moving from the right to the left. And this is going to be, this distance will be vt. Well, moving to the left with velocity v is the same as moving to the right with velocity minus v. Right? Moving west with a velocity of 10 meters per second is the same as moving east with a velocity of minus 10 meters per second, because you're moving in the minus east direction, which is west. Okay, so let's see. And now let's assume, so these charges, these are plus E, and these negative charges are minus E. You say these are protons in the top and the electrons on the bottom. So what is the current here? Well, if we're taking our current direction, we want to know what's the current flowing to the right. Then we would say, well, it's the number of charges per unit length times the actual charge in coulombs on each of those charged particles times its velocity to the right, which is minus v in this case. Well, notice what happens. You've got negative charge flowing to the right with a negative velocity. The two negatives cancel out and you get the same result. And number of charges per unit length times this fundamental charge times this absolute velocity v. In other words, negative charge flowing to the right is the same as, flowing to the left here. And the negative charge is flowing to the left, Negative charge flowing to the left is the same as positive charge flowing to the right. And in fact, in the early days of investigations into electricity, primarily in the 19th century, people didn't yet know about protons and electrons and neutrons. And so they didn't know what actually was going on down at the microscopic level. And that wasn't until the 20th century people figured that out. So in a piece of wire, it's actually typically the electrons that are flowing, creating the current. So it's really, if we say we have a current of 10 amps, 10 amperes, or we call it for short amps, 10 amps flowing to the right, actually what's happening is we got a bunch of electrons flowing to the left, carrying negative charge to the left, which is the same as positive charge going to the right. However, there are situations where positive charges are the ones that move. So for example, in the electrolyte of a battery, you can have positive ions carrying current. And in semiconductors, you can have both positive and negative charges moving, so-called holes and electrons. So instead of trying to figure out whether it's positive or negative charge moving, we just use what we call conventional current. Which is we assume it is positive charge moving to the right, regardless of what actually is going on microscopically. Okay, so that's current and the idea of conventional current. Now, for our purposes in this course, we're going to be concerned with two terminal devices. And here is a schematic symbol of that. A little box. And it has two terminals. Let's call it A and B. And we will be interested in the voltage drop between the terminals. That is the change in voltage going from A to B. Right? Remember, voltage tells you the amount of energy it takes to move a charge between 2 points. So in this case, the higher voltage, the higher potential is up here at A and the lower at B. If I took 1 coulomb of charge at point B and moved it to charge A, how much work would I have to do per unit charge? That would be the voltage V. And we'll have a current flowing, say, from A to B. Now, either of these values, V or I, could be negative, meaning that actually higher potential might be on terminal B rather than A. This is just our reference. These are just reference directions. So that if we have a positive voltage, it means that the voltage is higher at the plus than at the minus. And if we have a positive current, it means it's going in the direction of the arrow. A negative current would be going the opposite direction. A negative voltage would tell you that the potential was higher at the bottom than at the top. These are just reference directions. And the way we've drawn these, this is the so-called passive sign convention. And that means that the direction of positive voltage drop, right, I mean going from the higher to the lower potential, is equal to the direction of positive current flow. Or you could say that current is positive when it flows into the positive voltage terminal and out of the negative voltage terminal. Okay. So that would be a two-terminal device. Now we'll have three different types of two-terminal devices. We'll have resistors, capacitors, and inductors, and then we'll also have voltage and current sources. So we're going to talk about those more as we go along. Now let's look at something we'll define to be P is equal to V times I. And I'm going to claim that this is the power that is dissipated in this device. And we can see from the units, because voltage, right, we're going to say that a volt, 1 volt, remember, 1 volt is 1 joule per coulomb, and 1 amp of current is 1 coulomb per second. So multiply those together, and we'll have 1 volt times 1 amp is, well, here you got joules per coulomb and then coulombs per second. So the coulombs and the per coulomb cancel out, and that just leaves 1 joule per second, which is, that's power. That's 1 watt. So this has units of watts. It is the power that's being transferred to the device from the current, given the voltage drop. Finally, let's talk about how you measure voltage and current. So typically we use a digital multimeter like this one shown here. And you've got a dial where it allows you to measure voltage and current over here in amps, voltage in volts. This is resistance in ohms. We'll talk about that later on. And you would have 2 leads, a black one, which would be called the common, and then if you wanted to measure voltage, you put your red lead here or current here for amps, and so on. So suppose we have this circuit. We'll talk about this next lecture. A voltage source, like a battery, and then 2 devices, and we say these are in series, one after the other. And we want to know what the voltage drop across component or device D2 is, and the current I2 through it, so V2 and I2. We want to measure those. So how do we measure those? Okay, so the way we measure a voltage is we take our red positive lead that would come out of here, connected to the voltage terminal, and put that on what we want to be the positive terminal of the voltage drop, and then the black lead, which I've drawn here as blue just because it shows up better, we put that on the negative terminal. And then we would read off of this meter the values. So say it said 3 volts. That would mean that the potential here at the plus was 3 volts more, that means 3 joules per coulomb of charge, than the potential at the minus. Now if you took the 2 leads and you swapped them, well then you would be measuring the voltage drop from the bottom to the top, and the voltmeter would read minus 3 volts, meaning that the voltage drop from the bottom to the top is a negative, meaning that you really have a positive voltage drop from the top to the bottom. Now, to measure current, there's a subtlety here. To measure current, you've got to actually break the circuit and force all the current to flow through the current meter, or the ammeter, we would call it. You would, in this case, you'd plug into the A, or amp terminal, and here's what you do. You'd break the circuit so that current couldn't flow anymore through these wires, and then you would reconnect it through the ammeter, or ammeter. And now that current would flow through there, and then the ammeter could measure that full current, and now you can measure the current I2. Again, if this was positive, if say it read 1 amp, that would mean 1 amp is flowing into the red lead and out the black, or in this case shown it as blue lead. Now if you swap these leads, you would measure minus 1 amp, meaning that there's negative 1 amp flowing into the blue lead and out the red lead, meaning there's 1 amp going the opposite direction, right? So you can always change from positive to negative voltage and current just by swapping the 2 leads. Okay, and so that positive and minus, that's just a convention for what you call positive, right? It's just, in this case for the current meter, it's just the direction that you define to be positive is if it goes in the red lead and out the black or blue lead.